So Gibbs free energy which is denoted by the symbol G. Okay, by definition, Gibbs free energy is equal to H minus Ts. This is the definition of Gibbs free energy. G is equal to H minus Ts. From this, we can derive this standard equation dg equal to vdp minus sdt. This is actually standard equation. We can derive from this, okay, but I am not going to show that. Right now, the comical, but I will keep this in mind. From this definition of Gibbs free energy, we can derive this. And you know very well, this is applicable for closed system containing pure gas, right? And it is also a reversible process because we are using equal to symbol here, so it is applicable for reversible process. If any process occur in a reversible manner, you can use this formula, right? Now, from this formula, listen, if I keep pressure constant, right, at constant pressure, let me write simply like this: at constant pressure, if I pick pressure constant, this becomes 0. Therefore, what we get is dg equal to minus sdt. Or bring this dt to the left hand side, so we can write dou g by dou t at constant pressure equal to minus entropy. Okay, right? Similarly, at constant temperature, if we keep temperature constant, then this becomes 0. So we get dg equal to vdp, and bring the dp to the left hand side. So dou g by dou p at constant pressure equal to volume. Right? Listen. So dou, let's see, change in free energy with respect to temperature at constant pressure equal to minus entropy. So this is actually at constant temperature, right? So dou g by dou p at constant temperature equal to volume. Listen, this equation we use for n mole of gas or n mole of substance. If you have n mole of substance, you can use this formula. Okay, for 1 mole, we write this equation in a different form. Now 1 mole keppadi elduvonu aldren next page le you just copy down this or take a screenshot. Okay, now listen, I am going to write the same equation for 1 mole of gas. See, you know very well, dg equal to vdp minus sdt. Now observe pannunga, this equation is applicable for closed system containing pure substance, and the process should be reversible. Okay, now if I divide throughout by number of moles, I have told you this equation is applicable for n mole of substance. Now if I divide throughout by n, I will get equation for 1 mole. So divide G by n, Gibbs free energy by number of moles, divide volume by number of moles, divide entropy by number of moles. Okay, listen, for pure substance, observe carefully, for pure substance means it should not be a mixture. For pure substance, Gibbs free energy by number of moles is nothing but chemical potential. Okay, so chemical potential is nothing but molar Gibbs free energy, that is Gibbs free energy for 1 mole. Sometimes we can also write this as GM. GM means molar Gibbs free energy. It means Gibbs free energy for 1 mole of substance. So remember, for pure substance, what is chemical potential? Chemical potential is nothing but Gibbs free energy for 1 mole of substance. Okay, this is definition for pure substance. So in the place of G by N, I will put mu, change in chemical potential equal to, see, this is volume for N mole of gas. If I divide this by number of mole, I will get volume for 1 mole. Volume occupied by 1 mole of gas or 1 mole of substance is called molar volume. We represent molar volume by the symbol Vm. So Vm into dP minus, if you divide entropy by number of mole, we will get entropy for 1 mole of gas or 1 mole of substance, which is nothing but molar entropy into dt. Nalla observe pannunga. In the equation, this is applicable for n mole of gas, whereas this equation is applicable for 1 mole of substance or 1 mole of gas. Okay, now listen, as I said before, in this equation also we can make the same constants. See, if I keep pressure constant at constant pressure, if I keep pressure constant, this becomes 0. You will get change in chemical potential equal to Sm into dt. Bring the dt to the left hand side. So dou mu by dou t at constant pressure equal to minus Sm. Similarly, if I keep temperature constant, then this becomes 0. So you will get d mu equal to molar volume into dP. Bring the dP to the left hand side. So dou mu by dou p at constant temperature equal to molar volume. Okay, just note down these two are very important expressions. Sometime in the examination, they will give this left hand side. For a pure substance, change in chemical potential with respect to temperature at constant pressure equal to, 4 option kodupanga. Okay, so minus Sm is the answer. Right? Take down.
Molar volume na n by v.
Okay, listen. So first I will take this equation. Change in chemical potential with respect to temperature. With respect to temperature at constant pressure equal to minus Sm. Alright, what is the use of, what is this actually? Listen, if I plot chemical potential versus temperature, see, if I plot chemical potential in y-axis and temperature in x-axis, okay, we get a straight line passing, okay, we get a straight line with a negative slope. This is the slope. Right, we will get a straight line, right, with a negative slope. Okay, general you will get a negative slope. Why negative slope? Because molar entropy, Sm, molar entropy is always positive. Entropy cannot be negative, sir. Entropy எப்பயுமே positive தான். அப்போ இது பாசிட்டிவ்னா பாசிட்டிவ் இன்ட்டு நெகட்டிவ் இஸ் நெகட்டிவ். அப்போ என்ன வரும்னா ஸ்லோப் வந்து நெகட்டிவ் வரும். ஸோ S slope is negative here. Now listen, if I plot this for solid, liquid, gas, அப்போ எப்படி வரும்? Listen, now you need to compare molar entropy of a solid, liquid and a gas. Suppose I'll take some substance A. Assume that this substance exists in the solid form, liquid form and gaseous form. சார் நல்லா கவனிங்க, நான் ஏதோ ஒரு சப்ஸ்டன்ஸ் எடுக்கிறேன், அது சாலிடில் இருக்குது, லிக்விட்லேயும் இருக்கும், கேஸில் இருக்குன்னு வச்சுக்கோங்களேன். நான் முதல்ல சாலிட் எடுத்துக்கிட்டு, ஓகே, ஐ பிளாட் கெமிக்கல் பொட்டன்ஷியல் வித் டெம்பரேச்சர் கீப்பிங் ப்ரெஷர் கான்ஸ்டன்ட். அதை மறந்துடாதீங்க, ப்ரெஷரை கான்ஸ்டண்ட்டாக வச்சுக்கிட்டு நீங்கள் ஒரு கிராஃப் வரைஞ்சிங்கன்னா அந்த கிராஃபுக்கு பேர் ஐசோபாரிக் கிராஃப். ஐசோபார் ப்ரெஷரை கான்ஸ்டண்ட்டாக வச்சுக்கிட்டு நீங்கள் ஒரு கிராஃப் வரைஞ்சிங்கன்னா அந்த கிராஃபுக்கு பேர் ஐசோபார். ஸோ ஐ எம் பிளாட்டிங் ஐசோபார் ஹியர். இப்போ என்ன பண்ண போகிறேன், ஒரே சப்ஸ்டன்ஸ், சேம் சப்ஸ்டன்ஸு சாலிட்லேயும் இருக்கலாம், லிக்விட்லேயும் இருக்கலாம், கேஸ்லேயும் இருக்கலாம். அந்த மாதிரி கேஸில் ஓகே மியூ வெர்சஸ் டி எப்படி இருக்கும் அப்படின்னா, லெட் மீ ட்ரா ஹியர். சி mu versus T. Listen, compare the molar entropy of solid, liquid and gas. Molar entropy of solid, molar entropy of liquid, molar entropy of gas. If you compare, see, gaseous state has highest molarity, very high molarity, entropy compared to liquid. Liquid entropy is greater than solid. So, molar entropy பார்த்தீங்கன்னா கேஸ்க்கு தான் அதிகம். என்ட்ரோபி ஜாஸ்தியாக இருந்தால் கவனிங்க, இது ஸ்லோப்பு தானே, டி மியூ பை டி ஸ்லோப்பு. ஸோ ஸ்லோப் வந்து ஜாஸ்தியாக இருக்கும். அப்போ ஸ்லோப் யாருக்கு ஜாஸ்தியாக இருக்குன்னா கேஸ்க்கு. ஓகே, தென் லிக்விடுக்கு, தென் சாலிடுக்கு. ஸோ நான் ஒரு 3 ஸ்ட்ரெயிட் லைன் போடுறேன். இது ஸ்ட்ரெயிட் லைன் 1, இது ஸ்ட்ரெயிட் லைன் 2, இது ஸ்ட்ரெயிட் லைன் 3. இந்த 3 ஸ்ட்ரெயிட் லைனில் பாருங்கள், இதுக்கு ஸ்லோப் கம்மி, இதுக்கு ஸ்லோப் கொஞ்சம் ஜாஸ்தி, இதுக்கு ஸ்லோப் ஜாஸ்தி, ரொம்ப ஹை. ஸ்லோப்பு எப்போ ஹையாக இருக்கும்? மோலார் என்ட்ரோபிக்கு இல்லையா, மோலார் என்ட்ரோபி ஹையாக இருந்தால் ஸ்லோப் ஹையாக இருக்கும். யாருக்கு மோலார் என்ட்ரோபி ஹை பாருங்கன்னா பார்த்தீங்கன்னா கேஷியஸ் ஸ்டேட்டுக்கு மோலார் என்ட்ரோபி ஹை. gaseous state molar entropy high, therefore gaseous state must have high slope. So large slope in the line. So this should be for gas,
sir,
and this should be 1 second, sir. See, at this point, listen, these two straight line crossing at this point. In the point la cross panikudhu, and the point ku nera or temperature irukku illaya, right? This temperature is called melting point of the solid. Enagudhu, as you increase temperature, solid melts and become liquid. In the point la chemical potential of the solid is equal to chemical potential of the liquid. Chemical potential of the solid and chemical potential of the liquid becomes equal here. In the point la solid chemical potential, liquid chemical potential for same substance. See, for same substance, chemical potential in the solid phase, chemical potential in the liquid phase become equal, and that temperature is called melting point. Similarly, see, these two lines cross here, and this point, right? If you take the temperature corresponding to that point, it is called boiling point, TB. Adukku per boiling point solluvom. In the point la chemical potential of the liquid and chemical potential of the gas are equal. So in the temperature la liquid chemical potential, gas chemical potential equal agudho, that temperature is called boiling point. Okay, so remember, at the melting point, chemical potential of the solid and liquid are equal. At the boiling point, chemical potential of the liquid and gas are equal. Okay, observe pannunga. This is the second equation. Change in chemical potential with respect to pressure at a constant temperature equal to molar volume. Right. Now, if you compare molar, so if you plot chemical potential versus pressure, keeping temperature constant, see here, I'll plot chemical potential in y-axis and pressure in x-axis. I am going to keep temperature constant. Listen, if you keep temperature constant and if you draw any graph, that graph is called isotherm. Temperature constant வச்சிட்டு நீங்க வரையற கிராஃப்க்கு பேரு isotherm சார், நோட் பண்ணிக்கோங்க. It is called isotherm. Now, if you compare, suppose I take some substance A, assume that that substance exists in the solid form, liquid form, as well as in the gaseous form. If you compare molar volume, molar volume of solid is very low compared to molar volume of liquid. Okay, actually idukku romba periya difference irukadu, but molar volume of gas is very large. Molar volume of gas is very large. See, molar volume is nothing but slope of this graph. Dou mu by dou p da mu versus p oda slope nu solluvom. Okay, ipo slope vandu positive ah irukku, gavanunga, this is for solid will increase, right? ஏன்னா ஸ்லோப் பாசிட்டிவ்ன்றதுனால கெமிக்கல் பொட்டன்ஷியல் வெர்சஸ் ப்ரெஷர் பிளாட் பண்ணிங்கன்னா ப்ரெஷர் இன்க்ரீஸ் பண்ண ஓகே, கெமிக்கல் பொட்டன்ஷியல் வில் இன்க்ரீஸ். திஸ் இஸ் ஃபார் சாலிட் அண்ட் திஸ் ஒன் இஸ் ஃபார் லிக்விட். லிக்விடுக்கு ஸ்லோப் இன்னும் கொஞ்சம் அதிகமாக இருக்கும். கேஸ்க்கு இட் இஸ் வெரி ஹை. திஸ் இஸ் ஃபார் கேஸ். டேக் டூ. Take note. I repeat. See, this is the equation, one important equation which we discussed earlier. Now I am going to utilize this equation to calculate change in chemical potential for different cases. Okay, our goal is to find change in chemical potential. Right, sir, one more information. This change in chemical potential delta mu, right, is a measurable experimentally measurable quantity. One second. See, change in chemical potential is an experimentally measurable quantity. We can measure this experimentally. Okay. So left hand side mu2 minus mu1 is nothing but change in chemical that we can measure experimentally. Right. In the right hand side, see here we have molar volume. Molar volume for solid and liquid, okay, is very small. Is very small. For solid as well as for liquid, molar volume is very small. Okay, and molar volume for solid or liquid is usually, right, independent of pressure. Is independent of pressure usually. Solid liquid ஒரு சாலிட் எடுத்து நீங்கள் ரொம்ப ப்ரெஷர் கொடுத்தாலும் வால்யூமில் பெரிய சேஞ்ச் இருக்காது சாலிடில். இப்போ ஒரு இதாக சொல்கிற மாதிரி ஒரு அயன் ராட் எடுத்துக்கோங்க. அயன் ராட் எடுத்துகிட்டு நான் கொஞ்சம் ப்ரெஷர் கொடுக்குறேன். ப்ரெஷர் கொடுத்தா வால்யூமில் பெரிய சேஞ்ச் இருக்காது. ஸோ மோலார் வால்யூம் ஃபார் சாலிட் அண்ட் லிக்விட் இஸ் இண்டிபெண்ட் ஆஃப் ப்ரெஷர் ஜென்ரலாக சொல்லுவோம். சார் இட் இஸ் நாட் ஆல்வேஸ், இட் இஸ் தி ஜென்ரல் ஐடியா. So since it is, see, by changing the pressure P1 to P2, molar volume for solid or liquid, மற்ற கேஸ்க்கு நீங்கள் கேஸ்க்கு யூஸ் பண்ண முடியாது. கேஸ்க்கு மோலார் வால்யூம் சேஞ்ச் ஆகிடும். சாலிட் லிக்விடுக்கு மோலார் வால்யூம் இஸ் இண்டிபெண்ட் ஆஃப் ப்ரெஷர். ஸோ வி கேன் டேக் இட் அவுட். மோலார் வால்யூம் வெளியே வச்சுக்கோங்க. அப்போ இன்டகரல் டிபி வரும். இன்டகரல் டிபி இஸ் பி, அப்பர் லிமிட் P2, lower limit P1. So you will get P2 minus P1. Take note. Take note. And here this is very, very important. Since molar volume is very small, okay, this right hand side quantity is almost negligible. Okay, this is negligibly small. Let me write here. It is negligible. Negligible. So what is that? It means mu2 minus mu1 is nothing but delta mu, called change in chemical potential, is 0 for solids and liquids. Okay, close to, it's not exactly 0, it's almost 0. Why? Because molar volume for solid and liquid is very, very low. Okay, அதனால இந்த ரைட் ஹேண்ட் சைடு இருக்கு பாருங்க, இந்த ப்ரெஷர் சேஞ்சினால even if the P2 minus P1 is small, if even P2 minus P1 is small, then this product is very, very small. So we can neglect this. If neglect பண்ணா it is close to 0. So what is the conclusion? The conclusion is that in the case of condensed phase, solid liquid, okay, by changing pressure, right, by changing pressure change பண்றதுனால chemical potential பெருசா change இருக்காது. Okay, so chemical potential, there is no appreciable change. Let me write like that. There is no appreciable change. பெருசா சேஞ்ச் இருக்காது தான் மீனிங். there is no appreciable change in chemical potential, okay, by changing pressure, okay, for solids or liquids. Take note. Sir, புரியுதா பாருங்க. Yeah, now listen.
Sir, first முன்னாடி பேசி.
Now listen. Okay, now I'll take for gaseous state. In gaseous state, we separate gases as ideal gas and real gas. Or we discuss gases in two different ways. One is ideal, the other one is real. So first I'll take ideal gas. In the case of ideal gas, change in pressure, okay, na pressure change panna chemical potential la enna change varudhu at constant temperature adha paaka porom. Okay, now see, we know very well at constant temperature, change in chemical potential equal to molar volume into change in pressure. Okay, this equation we know very well. Change in chemical potential equal to molar volume into change in pressure. Okay, now what I am going to do, we have taken ideal gas here. For ideal gas, right, we can write for 1 mole of, because this equation is applicable for 1 mole, I have told you already. This equation is applicable only for 1 mole. So for 1 mole of ideal gas, for 1 mole of an ideal gas, right, for ideal gas numerical PV equal to nRT. N is number of mole, we have taken 1 mole, so RT. Now number of mole is 1 here. If we put number of mole 1, then this V is nothing, become molar volume. So PVM equal to RT. Then what is VM? VM equal to RT by P. I'll take this as equation number 1. Now I'll put this VM, okay, in equation number 1. Therefore, change in chemical potential equal to, in the place of VM, I'll put this value RT by P into dP. Or we can write d mu equal to RT. Keep RT as such. You know very well dx by x is equal to ln x. I'm sorry, d ln x. Dx by x is equal to d ln x. So dP by P can be written as d ln P. Take down. This is an important equation. Let me take this as equation number 2. This equation is applicable only for ideal gas. It is applicable only for ideal gas. Okay, take down. Now, d mu means small change. We need to find out for finite change. So, for finite change, delta mu. What is delta mu? Mu 2 minus mu 1. Okay, mu 2 minus mu 1. Right, that we need to integrate. After integration, we'll get this. Okay, so delta mu is equal to integral RT d ln P. Let the initial pressure be P1 and final pressure be P2. I am changing the pressure. Okay, I am changing the pressure, right? And how chemical potential changes. This is what we are going to discuss. Okay, take down. Listen. So change in chemical potential delta mu is equal to, see here R is constant. We are keeping temperature also constant. So RT, these are all constant. You can take it out. Differential of ln P. Okay, or differential. Let me take this as x. Okay, integral of dx is x. So integral of d ln P is ln P. Upper limit P2, lower limit P1. So we get, you take RT out, RT into ln P2 by P1. Okay, take down. Okay. And what is actually left hand side? Left hand side is chemical potential, final chemical potential minus initial chemical potential mu1. Mu2 minus mu1 is nothing but delta mu. What is mu2? Listen, at temperature T, we are keeping temperature constant. So, enna temperature vekkringa and the temperature T, and at final pressure P2. T temperature, P is pressure. At temperature T under pressure P2, the chemical potential is mu2. At temperature T and pressure P1, the chemical potential is mu1 is equal to RT ln P2 by P1. Now, only the delta mu expand panni kaamichirken. Final chemical potential minus initial. Adana delta mu. Now what I'm going to do, suppose if I take the initial pressure P1, if I take the initial pressure as P0, now initial pressure P0 வைக்கிறேன். What is P0? P0 is nothing but standard pressure. Standard pressure. Okay, and standard pressure value you know, which is nothing but 1 bar. நான் இந்த initial pressure 1 bar எடுத்துக்கிறேன். அப்போ என்ன பண்ணலாம், P1க்கு பதிலா 1 ன்னு போட்டுற வேண்டியதான். And what about P2? I'm going to write P2 simply as P. Because P1 is 1, I'm going to write P2 as P. So this equation becomes, listen, mu2 at temperature T and some pressure P. In the place of P2, I'll put P. Minus mu1, so nalla observe பண்ணுங்க, at temperature T. Now P1 is equal to 1 bar. Listen, chemical potential at 1 bar pressure is nothing but standard chemical potential. Okay, equal to RT ln P. In the place of P2, you put P. P2 க்கு பதிலா P போட்டுருங்க. P1 is 1 bar, so you need not put that. Okay, right? And this is also an experimental measurable quantity. We write simply this as delta mu. So delta mu is equal to RT ln P. Once again we have come to the same equation. Okay, take two. For real gas. Okay, so third scene. So how to understand change in chemical potential by changing the pressure of a real gas. You take a pure real gas. Okay, pure gas. Okay, listen, as I said before, at constant temperature, sir, at constant temperature, change in chemical potential d mu equal to molar volume into dP. This we know, right? Take this we know. D mu equal to Vm into dP. This is at constant temperature. Even for ideal gas, we started the derivation from this equation. So nalla observe பண்ணுங்க, for ideal gas, for any ideal gas, whatever ideal gas you take, for any ideal gas, molar volume is equal to RT by P. This is the single equation we have for all ideal gas. எல்லா ideal gasக்கும் molar volume equal to RT by P தான், simple. இப்போ எனக்கு ப்ராப்ளம் என்னன்னா, for real gas, what is the expression for molar volume? molar volumeக்கு என்ன expression பார்த்தீங்கன்னா, listen, real gasக்கு van der Waals equation இருக்கு, Berthelot equation இருக்கு. Okay, we have van der Waals equation, Berthelot equation, okay, virial equation. There are so many equations available. So molar volume, okay, will be different for different real gas, and you will get a complicated expression, right? If you use molar volume for real gas, okay, it becomes very complex. It becomes very complicated equation. We usually get a very complicated equation, very complicated. Therefore, in the place of molar volume, we cannot use RT by P. Suppose if we use RT by P, listen, for ideal gas, what we get? Ideal gas, d mu equal to RT into d ln P. I have told you, this is applicable only for ideal gas. d mu equal to RT into d ln P. This is applicable only for ideal gas. Okay, but for real gas, we don't have a single expression for molar volume. நமக்கு molar volumeக்கு ஒரே ஒரு expression கிடையாது. We have many expressions for molar volume. Okay, some real gases follow van der Waals equation. Some other real gases follow Berthelot equation. Okay, there are so many equations available for real gas. Real gasக்கு நிறைய equation இருக்கு. ஒன்றுத்துக்கு Vmக்கு ஒரு ஃபார்முலா வரும். ஒவ்வொரு ஃபார்முலா நீங்கள் சப்ஸ்டிட் பண்ணி பார்த்தீங்கன்னா ரியல் கேஸ் படிக்க முடியாது. இட் பிகம் வெரி காம்ப்ளெக்ஸ். அப்போது என்ன பண்ணுறது, டு மேக் திஸ் கான்செப்ட் ஈஸி டு அண்டர்ஸ்டாண்ட், scientist G and Lewis introduced a concept of fugacity, right? G and Lewis என்ன பண்றாரு, fugacity-னு ஒரு கான்செப்ட் இன்ட்ரோடியூஸ் பண்றாரு. அவர் என்ன பண்றாரு, you take this equation as such, like ideal gas, you keep this equation as d mu equal to RT d ln. Instead of pressure, you put some function, say F, where this F is called fugacity. Take note. It is called fugacity function. I am going to integrate this. If you integrate both sides, change in chemical potential. Okay, this is chemical potential. Okay, before going to that, I'll give this point, then I'll go. Listen. Suppose assume that the initial pressure is P1 and the final pressure is P2. Sir, observe carefully. Initial pressure P1, final pressure P2. At the initial pressure P1, let the fugacity be F1. At the final pressure P2, let the fugacity be F2. Okay? P1 pressure la ஒரு fugacity, P2 pressure la ஒரு fugacity இருக்கும். Listen, இப்போதைக்கு இது ரெண்டும் unknown. These two are unknowns. We don't know what is the value of these. They are unknowns. I know pressure P1, P2 and தெரியும், but I don't know what is F1 and F2. Okay? Take note. Now what I am going to integrate both sides. So integrate d mu, right? Lower limit is F1 to F2 here, and in the right hand side RT into d ln F. I'll integrate this from F1 to F2. I'm integrating both sides. Okay, just take note. In the left hand side, the next page I'll show you. So in the left hand side, if you integrate d mu, you will get mu. Upper limit, lower limit substitute, you will get chemical potential mu2 in the final state at temperature T and at pressure P2. Okay, then minus chemical potential in the initial state at temperature T and at pressure P1. This is chemical potential in the final state. This is chemical potential in the initial state, is equal to RT. Just check the right hand side. We have RT d ln F. If you integrate d, integral dx is x, no. So integral d ln F is ln F. Upper limit F2, lower limit F1. So we get RT into ln F2 by F1. Okay, observe this carefully. Right now I am going to give you one important idea. Listen, this we can get experimentally. Sir, observe pannunga. This is nothing but delta mu. This we can measure experimentally. Experimentally measurable. Okay, mu2 minus mu1 is experimentally measurable quantity. You can measure this. Left hand side I know, I can measure experimentally. If I know the left hand side, okay, listen, I have F2 and F1. I don't know what is F1 and I don't know what is F2. But left hand side எனக்கு தெரியும், temperature தெரியும், R எனக்கு தெரியும். அப்போ இந்த F2 F1 ல if I know any one, F1 தெரிஞ்சிருந்தா நான் என்ன பண்ணலாம்? If I know F1, that's the idea. If I know F1, I can find F2. Now listen, if F1 is known, then we can find F2. So what scientists did was, listen. Okay, let us take some reference state. ஒரு reference state எடுத்துக்குவோம். அந்த reference stateல okay, fugacity F1க்கு ஒரு வேல்யூவை ஃபிக்ஸ் பண்ணுவோம். We'll assign some value. Okay, so they took a reference state initially, reference state. They took a reference state. Okay, what is a reference state? Very simple. Listen, when pressure approaches very low value, when pressure approaches very low, you know very well, இது ரொம்ப basic concept. When pressure approaches very low value, okay, what happens is that real gas starts to behave like ideal gas. Observe this carefully. At low pressure, real gas starts to behave like ideal gas. Starts to behave like ideal gas. Okay. Now, listen. So, what I am going to do, what's the meaning here is that, listen, suppose if I choose initial pressure P1, if it is very low, if I choose initial pressure P1 is very low, at very low pressure, real gas behaves like
ideal gas.
Real gas behave like ideal gas. For ideal gas, observe carefully. If it is ideal gas, see this equation. If it is ideal gas, then F should be. See, this is for ideal gas. If this equation, if your real gas behave like ideal gas, F becomes
Pressure.
F becomes equal to pressure. Yes, you are right. So, if P1 is very low, then F becomes equal to P. F becomes equal to P. So, I can put in the place of F1, I can put P1 itself. F1 இருக்கிறது P1 போடலாம். Okay. Now, so P1 should be a low value, yeah. But for each and every gas, right? See, for each and every gas, you need to identify at what pressure, at what P1, the gas behaves like ideal gas. It is somewhat tough. So what scientists did was, instead of a reference state, okay, they took an hypothetical state. See, they took a standard state. Standard state எடுத்துக்கிட்டாங்க. என்ன எடுத்துக்கிட்டாங்கன்னா, listen, if P1 equal to P0, P1 இருக்குல்ல, initial pressure, if it is equal to standard pressure, what is standard pressure? You know very well, 1 bar. See, 1 bar is actually a very low pressure. 1 bar pressure is a low pressure. So, when P1 equal to P0, okay, scientists assumed that real gas behave like ideal gas. Real gas behaves like ideal gas. It is an hypothetical state. Okay, it's an hypothetical one. So, they assumed that if P1 is P0, then the real gas behave like ideal gas. Therefore, what I am going to do in this equation, observe carefully. In this equation, what I am going to do, mu 2. So, I am going to put P1 equal to P0. P1 equal to P0. When P1 equal to P0, then P1 becomes equal to F1. Yeah? Yeah, now at 1 bar pressure, most real gases behave like ideal gas. But P1 is nothing but F1. So, in the place of F1, I can put P1. And now P1 is equal to 1 bar. Okay, because P1 is nothing but P0. So, P1 க்கு பதிலா 1 bar போடலாம். or F1 க்கு பதிலா 1 bar போடலாம். Okay, and F2 இருக்கு பாருங்க, F2. We don't know what is F2. Okay, let me take that value simply as F instead of F2. இனிமே நீங்க F2 போட வேண்டாம், F1 வச்சுக்கோங்க. So, what happened to this above equation? See, I'll take this equation as equation number 1. Okay, now what will happen to this equation? Right? Just take down this. Okay, so chemical potential at temperature T and at pressure P2 minus standard chemical potential, because we have taken P1 as 1 bar. So, you will get standard chemical potential equal to RT ln. You replace F2 as F and F1 as 1 bar. Because we have taken standard state as the initial state, and this difference is nothing but delta mu. Delta mu, you know, delta mu is experimentally measurable. So, since you can measure this experimentally, when a gas undergoes change in pressure, you take a real gas, change the pressure of the real gas P1 to P2. Okay, now what is the change in chemical potential? due to change in pressure. Yes, this we can obtain experimentally. Since this value is known, we can find what is the fugacity in the final pressure P2. Initial pressure is 1 bar, that I know. Now the question is, what is the fugacity in the final pressure? Yes, you measure this delta mu for P1 to P2, substitute the value here and divide by RT, you will get ln f. From ln f we can find the fugacity. So you can find the fugacity of a gas, of a real gas, right, at any pressure P, at any pressure P. Okay, take note. Based on this, we are going to define fugacity, right? What is that? Listen, in the case of ideal gas, so observe this carefully. For ideal gas, okay, fugacity is directly proportional to pressure. So please listen carefully. Fugacity is proportional to pressure for ideal gas. If I equate this, equate panna sir.
Add one constant.
Or constant second, yeah, that proportionality constant is taken as 1 into P. Therefore, you will get F is equal to P. For ideal gas, fugacity and pressure are one and the same. For ideal gas, fugacity and pressure are one and the same. You fugacity ku badila pressure use pannalam. Ideal gas ku, okay, take note. Because proportionality constant is 1. 1 under the constant dane. Proportionality constant is a constant. Yes, 1 also constant. Right, take note. Now, for real gas, observe carefully. I am going to define fugacity. For real gas, fugacity is not proportional to pressure. Very important line, note down. In the case of ideal gas, they are proportional and proportionality constant is 1. In the case of real gas, they are not proportional to pressure. F is not proportional to pressure. Okay? Right? Since F is not proportional to pressure, the quantity F by P sir, observe carefully. Suppose if F is proportional to pressure, then F is equal to, I will take some constant K into P and I will bring this P to the left hand side. So F by P equal to constant, correct? If F is proportional to P, I can write F by P equal to constant. Now what I am saying is that F is not proportional to P. Therefore, F by P is not a constant. It is not a constant for a gas. Or I can say F by P is some coefficient called fugacity coefficient. Take note. Fugacity coefficient. This gamma is called fugacity coefficient here. Remember, gamma is not constant. Even for a given gas, ஒரு கொடுக்கிற கேஸ்க்கு fugacity constant கிடையாது. ஏன்னா Fம் Pயும் proportional கிடையாது. Okay, but this is well known. If pressure approaches low value, sir, observe carefully. Okay, நம்ம ஒரு pressureக்கு for a given pressure, what is the fugacity? We can find out like experimentally. That's what I told you. For a given pressure P2, we can find what is the fugacity. Right? Now, listen. I'll take some pressure P. I can measure fugacity. Yes, good. Now, if the pressure is very, very low, what will happen? The gas starts to real gas starts to behave like ideal gas.
Ideal gas.
If they starts to behave like ideal gas, then F by P become equal to 1. Yeah?
Yeah, F is equal to 1 for ideal gas.
Yes. Therefore, this is the definition. Limit. The limit when pressure approaches low value, pressure approaches 0. Okay. This F by P becomes equal to 1. This is the definition for fugacity. Take note. Just note down. Listen. For ideal gas, fugacity equal to pressure and gamma equal to 1. Because gamma is nothing but F by P. For ideal gas, F and P are equal, therefore gamma equal to 1. For real gas, okay, F and P are not equal. F and P are not proportional. Gamma is not equal to 1. 1 kadayadu. Okay, actually speaking, listen, this is very important point. For most real gas, nariya real gas enna varuna, in general, listen, fugacity value is less than pressure adha irukum. In general, pressure of gas விட fugacity value கம்மியா இருக்கும். எந்த மாதிரி கேஸுக்குன்னு பார்த்தீங்கன்னா உங்களுக்கு தெரியும், மோஸ்ட் கேஸஸில் அட்ராக்டிவ் ஃபோர்ஸஸ் தான் இருக்குது. ஓகே, இஃப் there is an attraction between molecules, right? Okay, if attraction or attractive force, if attractive force exists, okay, in gaseous state between molecules, ஒரு மாலிக்யூலுக்கு இன்னொரு மாலிக்யூல் நடுவில் அட்ராக்ஷன் இருந்தால், ஓகே, அந்த மாதிரி கேஸில் ஃபியூகாசிட்டி வேல்யூ லெஸ் தென் ப்ரெஷராக தான் இருக்கும். எஸ், நிறைய கேஸில் அட்ராக்ஷன் தான் இருக்குது. பட் ஃபார் சம் கேஸஸ் லைக் ஹைட்ரஜன் கேஸ், ஹீலியம் கேஸ், இதெல்லாம் இருக்குங்க இல்லையா, இவங்களுக்கெல்லாம் ஃபியூகாசிட்டி இஸ் கிரேட்டர் தென் ப்ரெஷர்னு வரும். ஏன்னா இந்த கேஸ் எல்லாம் ரிப்பல்சிவ் ஃபோர்ஸ் இருக்கும். ஓகே, இன் திஸ் கேஸ் தேர் இஸ் a repulsive force. ஸோ ஞாபகம் வச்சுக்கோங்க, if gas molecule, between gas molecule, if attractive force exists, then fugacity will be less than pressure. If repulsive force exists, then fugacity is greater than pressure. Fugacity never equal to pressure for a real gas. Okay, take two. See, for real gases, fugacity and pressure are equal and fugacity coefficient is 1. For ideal gases. For real gas, fugacity coefficient is not equal to 1. It should be either less than 1 or greater than 1. Okay, listen, for most gases in general, fugacity is less than pressure. If F is less than P, gamma will be, can anyone tell me what will be the value of gamma? Will it be less than 1 or greater than 1? Let me write in the next page. See here, what I am trying to say. Number 1, listen, if attractive force exists between molecules, if attractive force exists between molecules, okay, if there is attractive force, right, then fugacity will be less than pressure. Okay, I have told you already. Now, if F is less than pressure, then gamma, what is gamma? Gamma is F by P. Now, which is low? Fugacity is low. So, numerator is low, denominator is high, which means gamma should be less than 1. For real gas, in which attractive force exists between molecules, gamma value will be less than 1. Number 2, if repulsive force exists, between molecules, in this case fugacity value greater than pressure. Okay, if see, fugacity is the numerator, pressure is the denominator, right? Since F is greater, so gamma value will be greater than yes, take down. So determination of fugacity, take down. Determination of fugacity of a real gas. Okay, so what I am going to do, listen, what I am going to do, there are several methods available. First I will take a method using residual volume. Using residual volume, we represent residual volume by the symbol alpha. Using residual volume, we are going to measure fugacity. What is residual volume? See here, residual volume alpha is equal to molar volume of the ideal gas, I'll put Ig, ideal gas, minus molar volume of the real gas. For real gas, we write simply Vm. If you write Vm, it is real gas. Ig put ideal gas, that's all. So, observe carefully, I'm taking molar volume. What is the meaning? See, observe carefully, observe carefully. I'll take in one container, I'll take an ideal gas, okay, with some piston like this, and in another container, I'll take some real gas, okay, with some piston, okay. Here I have ideal gas, here I have some real gas, right? Observe carefully, observe carefully. Initially, let the pressure be P1, temperature be T. Similarly, here also pressure is P1, temperature is T. ரெண்டு பேருக்கும் pressure same, ரெண்டு பேருக்கும் temperature same வைக்கிறேன், volume same இருக்குமா? Are the two volumes equal?
No, sir.
Definitely,
No, sir.
very good. Definitely not. Why? Because in real gas, attraction or repulsion will exist. Because of that, volume will be different. Now, at some pressure P1, ideal gas, 1 mole of ideal gas occupies some volume, 1 mole of real gas occupies some volume. We can measure the volume. Experimentally, we can measure the volume. So, what is the volume of the ideal gas minus what is the volume of the real gas? You will get alpha. Right? Now, you change the pressure. Suppose you change the pressure as P2. Keep the temperature as such. See, I'll take the same container, I'll increase the pressure. Okay, just push the piston down. Okay, I'll increase the pressure. Now the pressure is P2, but temperature remains same. Here, you just compress the gas. Okay, here also, and keep the pressure as P2, temperature T. So this pressure and this pressure are same. Now at pressure P2, again measure alpha. சார் நல்லா கவனிக்கணும், நான் பேசுறது புரிதா பாருங்க. முதல்ல P1 ப்ரெஷரில் ரெண்டு பேரும் வைக்கிறேன், ரெண்டு பேருக்கும் டிஃப்ரென்ஸ் கண்டுபிடிக்கிறேன், வால்யூம் டிஃப்ரென்ஸ், ஒரு ஆல்ஃபா வரும். நவ் டெம்பரேச்சர் அப்படியே வச்சுக்கோங்க, ப்ரெஷர் சேஞ்ச் பண்ணுங்க, இன்க்ரீஸ் த ப்ரெஷர் ஹியர் ஆல்சோ, ஸோ தட் டூ ப்ரெஷர் ஷுட் பி ஈக்குவல். ஓகே, அட் ப்ரெஷர் P2, what is the difference? You find out. Similarly, for various pressures P1, P2, P3, P4, P5, நிறைய டிஃப்ரெண்ட் ப்ரெஷரில் என்ன பண்ணுறேன், இந்த வால்யூம் டிஃப்ரென்ஸ் கண்டுபிடிக்கிறேன். ஸோ ரிமெம்பர், ஆல்ஃபா இஸ் கால்ட் ரெசிடுவல் வால்யூம். வி கேன் மெஷர் எக்ஸ்பெரிமெண்டலி. இட்ஸ் அன் எக்ஸ்பெரிமெண்டலி மெஷரபிள் குவான்டிட்டி. Experimentally measurable. Is this clear? Any doubt in this? Doubt irka?
Sir, your pressure எப்படி vary ஆகுது? இந்த ஃபைனலா சொன்னீங்களா சார்?
நான் pressure நான் தான் இன்க்ரீஸ் பண்றேன். piston இருக்குல, piston புஷ் பண்றேன்.
ரெண்டுத்துக்குமே ஈக்குவல் பிரஷரா சார்?
piston புஷ் பண்றேன். புஷ் பண்ணதுக்கு அப்புறம் இங்க வர பிரஷர் இங்க வர பிரஷர் ஈக்குவலா வச்சுக்கணும்.
ஓகே சார்.
பிரஷர் ஈக்குவலா இருக்கும், ஆனா வால்யூம்
is not same.
Volume is not same. Okay. Now listen. So I am going to plot alpha versus P. Let me show that. Listen, நல்லா observe பண்ணுங்க. I am going to plot alpha versus P. Plot பண்றேன். Listen, when the pressure is low, you will get some alpha value. As pressure increases, alpha decreases. You will get a graph like this. Okay, take down. This is experiment's graph. It's an experimental graph. Okay, so that's the important point. Keep in mind. I'll go back to that equation. Alpha is equal to molar volume of the ideal gas minus molar volume of the real gas. Okay, now listen. We know very well d mu is equal to V molar volume into dP. I'll take this as equation number 1. This we know. Okay, this is at constant temperature. Right? We also know that d mu for a real gas is equal to RT into d ln F. This also we know. See, in both the equation, left hand sides are equal, so I am going to equate the right hand sides. So RT d ln F is equal to molar volume of the real gas into dP. Molar volume of the real gas. Now listen, you see the previous equation, alpha minus Vm. Okay. Now here I can write this as, what is the molar volume of ideal gas? Ideal gas equation I know. PVm equal to, for 1 mole, right? PVm equal to RT. Then what is Vm?
RT.
What is Vm?
RT by P.
P. This we know.
RT by P.
But for real gas, I don't know what is the expression for molar volume, because different real gas follow different equation. Okay, take note. Now I'll interchange this. I'll write an expression for molar volume. Okay, I'll show it in the next page. So molar volume is equal to RT by P minus alpha. Is this clear? Any doubt? I'll take this as equation number 3. Now what I'm going to do, I'm going to plug this value here. So what we get is RT d ln F equal to RT by P minus alpha into dP. Okay. Bring this RT to the right hand side and divide inside. Okay, you will get d ln F is equal to, so if you bring RT here, you will get 1 by RT. If you multiply inside, RT cancel each other. So what we get is, and also multiply this, so I'll get dP by P minus alpha by RT into dP. Okay, so this is d ln F. dP by P is d ln P minus alpha by RT into dP. Okay, I'll bring this d ln P to the left hand side. Okay, or just write first this. Okay, we'll continue. Okay, take note. Listen. So this you know already, d mu equal to Vm into dP at constant temperature. You take this as equation number 1. You also know that for real gas, d mu equal to RT into d ln F. You take this as equation number 2. See, both the left hand sides are equal. Therefore, right hand side should be equal. So I am equating the two right hand sides. So RT into d ln F equal to Vm into dP. You take this as equation number 3. Then listen, alpha is equal to molar volume of ideal gas minus molar volume of real gas. Okay, and for molar volume of ideal gas, you put RT by P. Then rearrange that, you will get molar volume for real gas. So molar volume for real gas is nothing but RT by P minus alpha. Substitute this in this place. Okay, in the place of Vm, substitute this. Now bring RT, in the left hand side we have RT, bring it to the right hand side. So you'll get 1 by RT. This RT comes here as 1 by RT. Then multiply here and here. Okay, so if you bring it inside, RT cancel here, and here you'll get RT. Okay, and bring multiply with the dP also. So here you'll get dP by P. Here you'll get alpha into. Okay, yeah, take note. Now I'm going to integrate. Okay, I'll just finish off this. It's very simple. D ln F. Okay, from fugacity F1 to F2, I'm integrating this with the limit F1 to F2 equal to integral P1 to P2 d ln P minus integral. I'll take 1 by RT out, because RT is constant. P1 to P2 into alpha into dP. Okay, take note. Now observe this carefully. D ln F is ln F, upper limit F2, lower limit F1, so you'll get ln F2 by F1. Here I'll get ln P2 by P1. Here 1 minus 1 by RT, integral P1 to P2 alpha into dP. You keep this as such. Now what I'm going to do is that, let us assume that P1 equal to P0. P1 means initial pressure, which is, I'm going to take it as 1 bar. Okay, if P1 equal to P0, right, then your gas starts to behave like ideal gas, then P1 and F1 become equal. What is F1? F1 is the fugacity at pressure P1. F2 is the fugacity at pressure P2, correct? So if you take P1 as a low pressure, 1 bar pressure, then P1 and F1 become equal, right? So you can write this and I also going to write, listen, I'm also going to write F2 simply as F, P2 simply as P hereafter, because this P1 become 1 bar now, P1 become 1 bar and F1 also become 1 bar because I'm sorry, once again. So in the place of F2 I'll put F, in the place of P2 I'll put P. So what we get is, listen, ln F, this become ln, because F1 is 1, P1 F1 are equal, since P1 is 1 bar, F1 also 1 bar, so ln F equal to, here I'll get ln P minus 1 by RT integral, P1 is 1 bar 1 and P2 is P into alpha into dP. Okay, I'll bring the ln P to the left hand side. So ln F minus ln P can be written as ln F by P equal to minus 1 by RT integral. See, we have to integrate from 1 to P. Suppose if we take that low pressure, okay, just for calculation purpose, I am going to take it as 0 to P into alpha dP. You won't get a big change here, okay. You have to integrate from 1 to P, right? If you integrate from 0 to P, nothing going to change, okay, or the change is negligible. You need not worry about that, okay. So ninga in the equation eduthikalam. What is the importance of this equation? Listen, at pressure P, at some pressure P, what is the fugacity we can calculate? How? Listen, if you know this integral, okay, what is this integral? See, very simple. I have given this already. See, alpha versus pressure plot we know. This is experimental plot. Now, you take some pressure P. So, in this pressure axis, you take some pressure P. In this pressure, you draw a line and now find the area under this curve. This area you can find experimentally, which is equal to integral 0 to P alpha into dP. This integral is nothing but the area under the curve up to the pressure P. Okay, this area we know, RT we know, pressure we know. Okay, pressure namakku theriyum. Appo yarukku mudichalam?
Fugacity
So
conditions.
fugacity at this pressure we can find out, correct? Suppose we want fugacity at this pressure. In the pressure இது P1 வச்சுக்கலாம். இது ஏதோ pressure, sorry, P2. இது P2 prime வச்சுக்கலாம். P2 prime வேணும்னா find the total area. Right? So whatever pressure you give, for that pressure I can find the fugacity of the gas using this expression, because this is the experimental quantity. You can find it from the graph, experimental graph. If you know this value, R is constant, temperature is constant, we know all these values. Pressure also, if suppose we give some 50 atmosphere pressure, yes, for the 50 atmosphere, what is the value of fugacity we can find out. Okay, take note.